Hey everyone. So in the last video, we took a look at how modes are connected to the thermal energy of a substance. We found that the total thermal energy of a substance is always divided evenly between all the modes in the substance. Every single mode has the same amount of thermal energy stored inside of it. That thermal energy is given by this equation. It probably doesn't surprise us that the thermal energy stored in a single mode depends on the temperature of a substance. But let's think about this the opposite way. Let's now think about how temperature depends on the thermal energy of a mode. To start, let's think about the total thermal energy of a substance. It's probably not surprising that the total thermal energy of a substance is just the amount of thermal energy in each mode multiplied by the number of modes. But let's ask a different question. What is the change in thermal energy for a substance given a change in temperature? Well, it's not that complicated. The number of modes and the 1/2 kb in this equation are constants. They don't change as thermal energy changes, but temperature does change. And so we end up with this. The change in the thermal energy of a substance is just equal to the number of modes in the substance multiplied by the change in thermal energy for each individual mode. But we're not quite at heat capacity yet. The heat capacity of a substance is equal to the change in the thermal energy of the substance divided by the change in temperature. Well, notice this equation both has a change in thermal energy and a change in temperature. So let's just divide. So what we end up with here is that the change in thermal energy divided by the change in temperature of a substance, in other words, the heat capacity of the substance, is equal to 1/2 times the number of modes in the substance multiplied by Kb, the Boltzmann constant. This is a perfectly good model of heat capacity, and it's testable. If we know the number of modes that a substance has, we can just plug that number into this equation to make a prediction for the heat capacity. Now, really briefly, I want to touch on the difference between heat capacity and specific heat. Specific heat is just the amount of energy that we need to add to a standard amount of a substance in order to change its temperature by 1 degree. This standard amount is usually 1 kilogram or 1 mole. Heat capacity is just specific heat multiplied by the amount of the substance. It's just the amount of energy that we need to add to a particular amount of the substance in order to increase its temperature by 1 degree. By particular amount, I just mean whatever the amount of the substance in our problem is. Specific heat doesn't change depending on the amount of the substance that you have. It only depends on the properties of the substance. As we've seen, this means that it only depends on the number of modes in the substance. Heat capacity, though, does depend on the amount of the substance you have. The more of the substance you have, the larger the heat capacity. So let's try to use our model to compute the molar specific heat for 1 mole of a solid. Notice I'm not saying specifically what kind of solid we're talking about. There's a reason for this. In our model of thermal energy, solids and liquids always have the same number of modes, no matter what kind of substance it is. A particle in a solid or liquid always has 3 directions that it can vibrate. Each of these vibrations has a potential energy mode and a kinetic energy mode associated with it, for a total of 6 modes. Now, of course, in real life, the story is more complicated than this, but this model actually does a pretty good job of predicting the molar heat capacity for a lot of substances. So let's do that real quick. This is the equation that we found. This equation just says that the change in thermal energy for a substance is equal to 1/2 times the Boltzmann constant times the number of modes for the entire substance times the change in temperature. Let's try to expand this out a little bit. Well, what is the total number of modes of the substance? Well, it's just equal to the number of modes per particle multiplied by the number of particles. What is the number of modes per particle? Well, for a solid or liquid, we immediately know the number. It's just 6, so let's plug that in. What about the number of particles? Well, like I said, we're looking to compute the molar specific heat of this substance. In other words, the specific heat of 1 mole. Well, we're looking to compute the molar specific heat of the substance, the heat capacity for 1 mole of this substance. So the number of particles is just 1 mole, Avogadro's number, so we can plug that in too. So we found that the change in thermal energy for 1 mole of a solid is equal to 1/2 times the Boltzmann constant times the number of modes per particle, which is 6, times Avogadro's number, which is the number of particles, times the change in temperature. But we need to take one more step. Remember, the heat capacity is equal to the change in thermal energy divided by the change in temperature. So let's just divide by the change in temperature. And here's our model for heat capacity. And here's our model for the molar specific heat of a solid, or for that matter, a liquid. It's just equal to 3 times the Boltzmann constant times Avogadro's number. This model turns out to work pretty well for quite a few substances. You're going to have the opportunity in DL to compare the predictions of this model to some actual results from an experiment. And you'll find that the prediction that the model creates is actually pretty good. Not perfect, but pretty good. Now, a really important thing that I want to say. Remember that this model that we've just built only works for solids and liquids. The reason is that the number of modes for a single particle in a solid or liquid is always exactly the same, just 6. Never changes as far as we're concerned in this course. For a gas, though, things get more complicated. You'll see it in DL, and as I talked about in the last video, there's a video I made last year that covers this topic in detail. But once we know the number of modes per particle, it becomes really easy to just apply this model of heat capacity. All we have to do is swap out 6 for, well, the number of modes per particle. And we swap out Avogadro's number for just whatever the number of particles in our substance is. So there we go. We've built a model for the heat capacity of a large number of particles based on the behavior of each of the individual particles in our substance. We've learned most of what there is to know about modes, about counting them, and how they influence the heat capacity of a substance. There's one other little thing, though, that we need to be aware of when we're thinking about modes, and we'll talk about that in the next video. See you then.